This is a coffee bean. In Colombia, coffee is not just a product, it is identity, it is culture, it is the work of thousands of families. Every bean carries a story, but today the bean tells a different one. A story about air, about carbon, and about one of the greatest engineering challenges of our time. Because while the bean represents life, the air around us contains nearly 420 parts per million of CO2. And despite global efforts, we are still not moving far enough. Direct air capture exists, but it is still too energy intensive, too inefficient at low concentration, and too difficult to scale. So we asked a different question. What if something so deeply rooted in Colombia could become part of the solution?
From an engineering perspective, the challenge is clear. At atmospheric conditions, the CO2 concentration is extremely low. This results in a very low driving force, which directly limits mass transfers and system efficiency. So, the real question is not, can we capture CO2, but can we do it efficiently under these conditions?
To answer that, we focused on fundamentals and we identified the dominant limitation: mass transfer resistance. Specifically, the resistance between the air and the adsorbent molecules. If the molecule never reaches the surface, nothing else matters.
So we changed our approach. We didn't start by designing a device. We started by designing the journey of a CO2 molecule, from free flow air into contact into catch.
This is where engineering changes everything. Our system is a compact direct air capture unit, designed within a 1 cubic foot constraint. At its core, we use a multi-channel monolithic structure. This geometry allows us to control 3 critical variables: surface area per unit volume, flow distribution, and pressure drop. We are not waiting for contact to happen, we are engineering it.
The monolith contains 19 channels, with a hydraulic diameter of 15 millimeters and a required area of 0.1 square meters. At an airflow rate of 9.4 liters per minute, the system operates under laminar conditions, with Reynolds numbers below 50. Mass transfer coefficients were estimated using Sherwood correlations, confirming external resistance as the limiting step.
From a transfer perspective, the system is governed by external mass transfer resistance, so our design focuses on reducing the thickness of the boundary layer by improving flow distribution and contact uniformity. We increase the mass transfer coefficient. This directly enhances capture efficiency and low carbon dioxide concentrations.
Our calculations show that the available transfer area exceeds the required area by a factor of 1.8, ensuring effective capture under operating conditions. In addition, the structured monolith design prevents channeling and ensures that air is evenly distributed across the entire system. This maximizes effective gas-solid interaction.
And because the system is modular, it can be scaled through a number of strategies, maintaining performance while increasing capacity.
Our construction process is structured in 3 stages: component fabrication, system integration, and final assembly.
First, we manufacture each individual component, the internal supports, airflow, channels, and compartments for the absorbent monoliths. Every piece is designed with precision, ensuring tight fitting and alignment to prevent leaks and optimize flow performance. Then, we move into the system integration. The absorbent monoliths are placed inside optimized chambers to maximize gas-solid contact, while the airflow system pipes, connections, and control valves are assembled to ensure uniform distribution. These valves play a critical role, allowing the system to alternate between capture and regeneration, enabling continuous operation. In parallel, we integrate the regeneration system. Electric heaters provide the energy required to release the captured CO2, while vacuum pumps reduce pressure, making the desorption process more efficient. The synchronization of this element is key to maintaining performance without unnecessary energy losses. Finally, we assemble a complete prototype. All subsystems are integrated in a compact cube, including electrical connections and sensors to monitor temperature and pressure.
The result is more than a prototype. It is a fully integrated modular system. designed not only to work, but to be replicated, escalated, and deployed in real-world conditions. Air is driven to the monolithic adsorber where CO2 is selectively captured on the engineered surface. Flow control allows the system to alternate between adsorption and regeneration. During regeneration, pressure is reduced and heat is applied, releasing concentrated CO2 for storage. This coordinated cycle enables continuous carbon capture using dual bed configuration.
Once the molecule reaches the surface, we must ensure it is captured. So we return to the origin, the coffee residues. We transform coffee waste
into engineered VHR. Through chemical activation, we increase surface area and create microporosity.
Then we functionalize the material to introduce chemical affinity for carbon dioxide. This allows us to combine two mechanisms, physisorption for capacity and chemisorption for selectivity. We are balancing thermodynamics and kinetics.
So we've performed a sustainable production route for the adsorbent. Coffee residues are transformed into engineered biochar through thermochemical processing, followed by chemical activation and functionalization steps. This integrated process ensures material performance, scalability, and alignment with the circular economy principles. But designing the material is only part of the solution.
To ensure continuous operation, we design a dual bed system, where one bed captures carbon dioxide, the other undergoes thermal regeneration. This eliminates downtime and ensures continuous productivity.
Safety was a fundamental design consideration. We identify and address multiple risks. Potential loss of containment mitigate through seal design, thermal risk, control generation temperatures were mandatory, and material stability because we need a chemical stable biochar.
The adsorbent is a structurally stable carbon-based material configured as a monolith, which eliminates risks associated with particle dispersion. The system operates under near-atmospheric conditions, significantly reducing mechanical and operational hazards. Thermal regeneration is conducted under controlled temperatures, well below the material's degradation limits, ensuring long-term stability. Desorbed CO2 is contained and directed to a dedicated storage volume, preventing accumulation in confined or under-controlled environments.
Additionally, no hazardous byproducts are generated during operation. Low-pressure conditions enhance operational safety for users. Modular scaling reduces risk during deployment and expansion. We design not only for performance, but for safety, reliable operation at scale. Using 40 grams of activated carbon, each module captures approximately 9.2 grams of CO2 per day under continuous operation, which translates to around 3.3 kilograms of CO2 per year per cube. But this is not a standalone device. It is a modular unit designed for a large-scale deployment. At a scale, a network of just 1,000 cubes could remove over 3 tons of CO2 annually, transforming coffee waste into a distributed carbon capture solution. This solution is not only technical, it is systemic. We developed a strategic alliance with the Alliance BioPTX, connecting coffee producers, biomass supply, academia, system design and validation, industry, scale, and implementation.
This creates a complete value chain, low-cost feedstock, modular deployment, and decentralized carbon capture. We are not just building a device, we're building a scalable solution.
From a cost perspective, our system is already competitive, but its real strength is how it improves with scale. Each module costs around $200 to build and captures approximately 3.3 kilograms of CO2 per year. This places us within our current DAC cost ranges, but with a fundamentally different approach. Because we are not optimizing for a single unit, we are building a scalable, distributed system designed for real-world deployments. This allows organizations to adopt carbon capture incrementally, visibly, and directly in their operation.
With 100 units, the cost drops to around $13 per ton, and at larger scale, it can reach values close to $1.6 per ton. While capacity increases linearly, the cost per ton decreases, making the system increasingly efficient.
This happens because our costs don't scale at the same rate as capture. Our adsorbent represents less than 2% of the total system costs, and our regeneration operates at just 450 degrees Celsius, significantly reducing energy consumption. This gives us a key advantage. We can scale without being constrained by material or energy costs, two of the biggest barriers in DAC technologies.
Each unit generates measurable capture data that can be aggregated and validated. So we're not just distributing hardware, we're building a network of capture nodes. From a business perspective, this creates two revenue streams: deployment for scaling units across locations and carbon removal services through verified measurable impacts. This positions Air and Tech in a rapidly growing market where organizations are not only committing to net zero, but are required to prove it. As we grow, costs decrease, data increases, and system value compounds.
So we don't scale by building bigger systems. We scale by being everywhere. Because the future of climate solution is distributed, measurable, and scalable.
This journey started with a coffee bean, a symbol of Colombia, of culture, of life. But through engineering, it became something more: a material, a reactor, a system, a solution.
We are transforming coffee into climate solutions for the world. We are Air and Tech.